If I told you the Wild West ran on technologies more sophisticated than most people realize, you'd probably picture cowboys and campfires, but they had engineering systems that powered entire industries, moved mountains, and connected a continent. The most shocking part? We actually forgot how most of it worked. Ready to feel humbled by what people built with zero electricity? Let's see what powered the frontier. When miners needed to extract coal from deep underground, they couldn't just flip a switch and turn on lights or ventilation. They had to engineer complete infrastructure systems using nothing but mechanical ingenuity and raw materials. Coal mining wasn't just digging holes. It was creating underground cities with their own transportation, air supply, and drainage. The shaft itself was an engineering marvel. Miners would dig vertical tunnels hundreds of feet deep, reinforcing them with timber frameworks that distributed the weight of millions of tons of earth above. These supports had to be precisely calculated. Too weak, and the mine would collapse, killing everyone inside. The horizontal tunnels branching from the main shaft created networks that stretched for miles underground. These passages had to maintain specific dimensions to allow cart traffic while minimizing the amount of material that needed to be removed. Every cubic foot of rock removed was rock that had to be hauled to the surface. Drainage was critical because underground water would flood mines constantly. Miners would dig sumps, collection points at the lowest areas where water would gather. The infrastructure to channel water to collection points was itself complex engineering. Track systems were laid throughout the mines for carts. These weren't simple rails. They had to handle grades, curves, and switching points, all while being strong enough to support tons of coal. The track gauge was standardized so carts could move throughout the entire mine network. Ventilation shafts were dug separate from the main shaft to create airflow. The principle was simple. Hot air rises, creating a natural draft that pulled fresh air down one shaft and pushed stale air up another. But calculating the shaft dimensions and positions to create adequate airflow required understanding physics that most miners learned through deadly trial and error. The entire coal mining infrastructure was designed as an integrated system where each component supported the others. Remove one element, and the whole operation would fail. This wasn't primitive digging. It was industrial-scale engineering that happened to work without any electricity. But coal sitting in the ground was worthless. They needed power to extract it, and that power came from an invention that changed everything. Stationary steam engines were the workhorses of Wild West industry. These massive machines converted coal into mechanical power that could lift tons, pump water, and drive machinery. And they did it all through principles of physics that are almost elegant in their simplicity. The basic concept was straightforward. Burn coal to heat water in a boiler. The water turns to steam, which expands with enormous pressure. Direct that pressurized steam into a cylinder with a piston, and the expanding steam pushes the piston with tremendous force. Connect that piston to a crankshaft, and you've converted linear motion into rotational motion that can power anything. But the engineering details were incredibly sophisticated. The boiler had to withstand pressures that could reach 200 pounds per square inch. Boiler explosions killed hundreds of workers throughout the Wild West era. The metal had to be thick enough to contain the pressure, but not so thick that it couldn't transfer heat efficiently. The valve system that controlled steam flow was a masterpiece of mechanical timing. Valves had to open and close at precisely the right moments to admit steam, allow it to expand, then exhaust it. This timing had to happen dozens of times per minute, continuously for hours or days. Governors were mechanical feedback systems that regulated engine speed. As the engine spun faster, centrifugal force would push weights outward, which would close the steam valve slightly, slowing the engine. This automatic regulation happened continuously, maintaining steady speed without any human intervention or electronics. The flywheel was a massive rotating disc that stored kinetic energy. When the piston pushed during its power stroke, the flywheel would absorb that energy. During the return stroke, the flywheel would release its stored energy to keep everything moving smoothly. Stationary steam engines were installed at mine sites to power hoisting equipment, pumps, and ventilation fans. They were placed at sawmills to drive the cutting blades. They powered stamp mills that crushed ore. Anywhere that required serious mechanical power, you'd find a stationary steam engine. The efficiency was terrible by modern standards. Maybe 10% of the coal's energy actually became useful work, but coal was cheap and abundant. So efficiency didn't matter as much as reliability. These engines would run for decades with proper maintenance. But stationary engines had one limitation: they couldn't move. The next evolution of steam power would change the West forever. Steam locomotives took the stationary steam engine and put it on wheels. This wasn't just a minor modification, it was a complete reimagining of what steam power could do. Suddenly, that mechanical power could travel. And with it, the entire economy of the West could move. The locomotive was essentially a mobile steam engine with a boiler, pistons, and drive wheels, all mounted on a frame that could roll on rails. But the engineering challenges were enormous. The boiler had to be strong enough to handle the pressure while light enough that the locomotive could actually move itself. The firebox where coal burned was positioned at the rear of the boiler. A fireman would shovel coal into this inferno continuously, maintaining the heat needed to produce steam. On a long run, a fireman might shovel several tons of coal. The physical labor was brutal and never-ending. The cylinders were mounted on either side of the locomotive with pistons that drove the wheels directly through connecting rods. Unlike stationary engines that use crankshafts, locomotives use the wheel itself as the crank, the connecting rod attached to a point offset from the wheel's center, converting the piston's back and forth motion into wheel rotation. The valve gear that controlled steam admission to the cylinders was visible on the outside of the locomotive. These complex linkages opened and closed valves with precise timing. The engineer could adjust the valve timing to control power and efficiency. Braking systems use compressed air. The engineer would release air pressure, which would push brake shoes against the wheels. This air brake system was revolutionary because it failed safe. If the airline broke, the brakes would automatically engage. This saved countless lives. Water and coal had to be replenished regularly. Water towers along the rail line used gravity to fill the locomotive's tender. A locomotive might need to stop every 50 miles for water and every 100 miles for coal. The power output was staggering. A large locomotive could produce over 3,000 horsepower. That's the equivalent of 3,000 horses, all from burning coal and boiling water. This power could pull trains weighing thousands of tons across mountain passes and through deserts. Railroads connected the West in ways that were previously impossible. Towns that were weeks apart by wagon became hours apart by train. The economic impact was transformative. But locomotives needed fuel, and getting that fuel required more steam-powered technology working in the forests. Water-powered sawmills turned trees into the lumber that built every town, mine, and railroad in the West. These weren't simple operations, they were sophisticated industrial facilities that could process thousands of board feet of lumber daily using nothing but flowing water. The water wheel was the heart of the operation. A stream or river would be diverted to flow over or under a large wooden wheel. The water's weight and momentum would turn the wheel, which was connected to a main shaft that ran into the mill building. Inside the mill, the main shaft drove a series of belts and pulleys that distributed power throughout the building. Leather belts would run from pulleys on the main shaft to pulleys on various machines. By engaging or disengaging these belts, workers could turn individual machines on or off. The saw itself was typically a large circular blade. The circular saw would spin at high speed, its teeth cutting through logs that were fed into it on a carriage. The carriage moved on rails, pushing the log through the blade at a controlled rate. The log carriage was a mechanical marvel. It held logs securely while allowing the sawyer to adjust the log's position between cuts. After each pass through the saw, the carriage would return, the log would be rotated, and another cut would be made. The output was enormous. A good water-powered sawmill could produce 10,000 board feet of lumber per day. That's enough to frame several houses. This industrial-scale production made building towns economically feasible. But lumber built the surface structures. Underground, miners needed different technology to extract precious metals. Stamp mills were the loudest, most violent machines in the Wild West. These mechanical monsters crushed ore into powder so fine that gold and silver could be extracted. The noise was so loud it could be heard for miles, and the ground would shake from the constant pounding. The basic principle was simple but brutal. Heavy iron stamps, each weighing hundreds of pounds, would be lifted and dropped repeatedly onto ore. The stamps were arranged in a row, typically 5 to 10 of them, each lifting and falling in sequence. The stamps were lifted by cams on a rotating shaft. As the shaft turned, the cam would catch the stamp and lift it. When the cam released, gravity would pull the stamp down onto the ore below. This happened dozens of times per minute for each stamp. The ore was fed continuously into the stamping area. Water was added to create a slurry that would flow out through screens once it was ground fine enough. The screens had tiny holes that only allowed properly crushed material to pass through. The power required was enormous. A large stamp mill might have 50 stamps operating simultaneously. Water wheels or steam engines provided this power, turning the main shaft that operated all the cams. The noise was legendary. Workers would go deaf from years of exposure. The constant pounding created vibrations that would damage nearby buildings. Towns with stamp mills were towns where you couldn't have a conversation without shouting. But the economic impact justified the noise. Stamp mills made gold and silver mining profitable by efficiently extracting precious metals from ore. Without stamp mills, most Western mining operations wouldn't have been economically viable. Speaking of moving massive amounts of material, miners developed a technique that was even more destructive than stamp mills. Hydraulic mining used water pressure to literally wash away mountains. This wasn't subtle or careful. It was industrial-scale destruction that moved more earth than any other mining technique in history, and it worked using nothing but water, gravity, and engineering. The system started with water collection. Miners would build dams and reservoirs high in the mountains, sometimes miles from the mining site. The elevation difference was critical because it created the pressure that made the system work. Water would flow from the reservoir through ditches and wooden flumes, maintaining elevation as it traveled toward the mining site. At the mining site, the water entered iron pipes that dropped steeply downward. As the water descended, gravity accelerated it and increased the pressure. The nozzle, called a monitor or giant, could be aimed at the hillside. When the valve was opened, water would blast out with enough force to knock a man off his feet from 100 feet away. This pressurized stream would cut through soil and rock like a knife through butter. Miners would direct the water at gold-bearing hillsides, washing away everything. The debris would flow into sluices, long wooden channels with riffles on the bottom. Gold, being heavy, would settle behind the riffles while lighter material washed away. The scale was staggering. A single hydraulic mining operation could wash away entire hillsides in weeks. Millions of cubic yards of earth would be moved, creating landscapes that looked like alien planets. The environmental destruction was total and permanent. The efficiency was what made it profitable. A few men with monitors could move more earth than hundreds of men with shovels. The gold recovery rate was lower than other methods, but the volume processed more than made up for it. But getting into hard rock required different technology that combined steam power with clever mechanics. Pneumatic drills revolutionized hard rock mining by replacing hand drilling with machine power. Before these drills, miners would spend hours hammering steel bits into rock by hand. Pneumatic drills could do the same work in minutes, using compressed air powered by steam engines. The system started with a steam-powered air compressor at the surface. This machine would compress air to high pressure. typically 80 to 100 pounds per square inch. The compressed air would be stored in tanks, then piped down into the mine. The drill itself was a marvel of mechanical engineering. Compressed air would enter the drill and push a piston back and forth rapidly. This piston would strike a steel bit dozens of times per second, driving it into the rock. The bit would rotate slightly between strikes, ensuring that each impact hit a different spot on the rock. This rotation was automatic, driven by the drill's internal mechanisms. The combination of rapid striking and rotation allowed the drill to bore through solid rock at impressive speeds. Multiple holes would be drilled in a pattern across the rock face. Once drilling was complete, the holes would be packed with explosives. The blast would shatter the rock, which would then be hauled away. The noise was deafening. The pneumatic drill's rapid hammering created a sound that would permanently damage hearing. Combined with the confined space of a mine tunnel, the noise was physically painful. Pneumatic drills increased mining productivity by a factor of 10 or more. Tunnels that would have taken months to advance by hand could be completed in weeks. This made deep mining economically viable. But drilling holes was pointless if the mine filled with water faster than you could work. Mine pumping systems kept underground operations from drowning. Water seepage was constant in most mines, and without effective pumping, tunnels would flood within hours or days. The pumps that solved this problem were engineering marvels that worked continuously, often for years without stopping. The most common design was the steam-powered piston pump. A steam engine at the surface would drive a long rod that extended down the mine shaft. This rod would move up and down, operating a piston pump at the bottom of the shaft. Deep mines required multiple pumping stages a single pump couldn't lift. Water more than a few hundred feet due to physical limitations. So miners would install pumps at intervals, with each pump lifting water to the next level. The volume of water pumped was staggering. A large mine might pump thousands of gallons per minute, every day. The pumps never stopped because stopping meant flooding. The reliability of pumping systems determined whether a mine was viable. Rich ore deposits were worthless if they were underwater. The ability to keep mines dry was as important as the ability to extract ore. But pumps and drills were useless if you couldn't move the ore to the surface, and that required the oldest power source in history. Animal-powered hoists and capstans used horses and mules to lift tons of ore from deep mines. This wasn't primitive technology. It was sophisticated mechanical engineering that multiplied animal strength through clever use of gears, pulleys, and leverage. The horsewhim was the most common design. A horse would be hitched to a long horizontal beam attached to a vertical shaft. As the horse walked in a circle, the shaft would rotate. This rotation would wind a cable around a drum, lifting a bucket of ore from the mine shaft. The gearing was critical. A single rotation of the horse's circle might turn the drum multiple times through gear reduction. This allowed the horse to lift loads much heavier than it could pull directly. The mechanical advantage was significant. The ore bucket would be loaded at the bottom of the shaft, then signaled to the surface. The horse would begin walking and the bucket would rise. At the surface, the bucket would be dumped, then lowered back down for another load. This cycle would repeat hundreds of times per day. The efficiency was surprisingly good. A horse could lift about half a ton from a depth of several hundred feet in a few minutes. For shallow mines, this was adequate. The simplicity was the advantage. No boiler to explode, no complex machinery to maintain. But once ore reached the surface and towns were built, settlers needed water, and they found it using technology that became an icon of the West. Windmills pumped water across the arid West, turning uninhabitable land into ranches and farms. These elegant machines captured wind energy and converted it into the vertical motion needed to operate a pump. And the wheel at the top caught the wind. Multiple blades were arranged around a hub. As wind pushed against the blades, the wheel would rotate. The tail vane kept the wheel facing into the wind, automatically adjusting as wind direction changed. The wheel's rotation was transmitted down a shaft to a pump at ground level or in a well. The rotational motion had to be converted to vertical reciprocating motion to operate the pump. This was accomplished through a crank mechanism. Storage tanks were essential because wind was intermittent. When wind blew, the windmill would pump water into an elevated tank. Gravity would then provide water pressure even when the wind wasn't blowing. The reliability was remarkable. A well-built windmill could operate for decades with minimal maintenance. Windmills transformed the West by making water available where it otherwise wouldn't exist. Ranches could be established far from rivers. Towns could grow in locations that had no surface water, but water wasn't the only thing settlers needed. They also needed to preserve food in climates where summer heat would spoil meat in hours. Ice houses provided refrigeration without electricity by using ice harvested in winter and stored for summer use. This wasn't just piling ice in a shed. It was sophisticated thermal engineering that could keep ice frozen for months despite outside temperatures exceeding 100 degrees. The structure itself was designed for insulation. Thick walls filled with sawdust, straw, or other insulating materials prevented heat transfer. The ice building would be partially underground, taking advantage of the Earth's stable temperature. Ice was harvested from frozen lakes and rivers during winter. Workers would cut blocks weighing hundreds of pounds using specialized saws. These blocks would be transported to the ice house and stacked carefully with insulating material between layers. The stacking pattern was critical. Blocks were arranged to minimize air gaps while allowing drainage of meltwater. Sawdust or straw was packed between blocks and around the entire stack. The thermal mass of the ice itself helped maintain low temperatures. A large quantity of ice created a cold zone that was self-reinforcing. The bigger the ice mass, the slower it melted. Large commercial ice houses could store hundreds of tons. The ice that survived summer was valuable. It would be sold to businesses and households for food preservation and cooling drinks. Ice delivery was a regular service in frontier towns. The technology worked so well that ice houses remained common until electric refrigeration became widespread in the mid-1900s. Some ice houses built in the 1800s still stand today, testament to the engineering that went into their construction. So there you have it. 11 technologies that powered the Wild West without a single watt of electricity. These weren't primitive solutions. They were sophisticated engineering systems that harnessed steam, water, wind, and animal power to build an entire civilization. The coal miners who dug in darkness, the engineers who designed steam locomotives, the millwrights who built water-powered sawmills, they all understood principles of physics and mechanics that we've largely forgotten. Makes you wonder what we're doing now that future generations will look back on and think was impossibly crude, doesn't it? The Wild West wasn't tamed by cowboys with guns. It was conquered by engineers with slide rules who figured out how to move mountains, connect a continent, and keep ice frozen in the desert, all without flipping a single switch.